We're going to discuss the first eigenvalue series method. I'm Justin Shaw, and I'll be presenting. So the motivation here is that the gamma and EOF error map methods together cover an enormous range of data sets, right? So the gamma method is for time series data sets where you have more time information than you have spatial information. And the EOF error map method is for the case where you have much more spatial information than time information. But as long as you have both space and time information, you can use one of these methods and find interesting times in your data set if they're there. So that's an enormous range of data sets, and it's not very restricted. So together, the gamma and EOF error map methods are very useful over a very wide range of possible applications. But we also want to consider ensemble data sets. And ensemble data sets are relatively rare. So ensembles are very, very important, theoretically speaking, but they're not usually run. And the reason is that clock time is limited, and it's typically spent on parameter space exploration or resolution instead of running ensembles, which is understandable. Both parameter space exploration and resolution increase are very desirable. But how do you know if an experimental result is an outlier? So let's say that you run one incredibly high resolution simulation at your given parameter set, and you get some crazy result, right? How do you know that result isn't a 1 in 1,000 or 1 in 10,000 or 1 in 100,000 event? You don't, because you only ran one simulation. And so obviously confidence in reproducibility would be significantly increased if we ran ensembles. And we hope people run more ensembles as parallelization architecture becomes the norm, because it's easier than ever. And so we made a method for identifying features in these data sets as well. So let's recap. What does EOF do? And you may recognize this density profile example from previous videos, where this wave is propagating from left to right. Okay, so output 1, output 50, output 100. And so when you run the EOF on a simulation of this type, what you're saying is, I'm going to do all the time outputs are going to be the ensemble members, and I'm going to do the EOF performed over time. Okay. In an ensemble data set, let's say you have 100 runs. What we're going to do instead is, instead of doing EOF over time in each run, we're going to do the EOF across the runs at single time outputs. Okay. So our ensemble is going to be made up of the outputs at a single time output for all runs, and we're going to do the ensemble across time at one time instead of across the runs at one time rather than across time at one run. So performing EOF at each time output produces a scree at each time output, right? So one of the outputs from the EOF algorithm is all the eigenvalues. And if you normalize these, you get the scree. And they are the rank ordered and normalized eigenvalues associated with all the eigenvectors. And so the first eigenvalue then serves as a proxy for the entire scree, because the first eigenvalue tells you what the first EOF captures as far as variance. Okay, so if the first EOF is 0.9, that means 90% of the variance in your EOF ensemble members is captured by a single EOF. So a large first EOF corresponds to variance being captured by only one EOF. And a small first eigenvalue corresponds to not much variance being captured by a single EOF, meaning more variance needs to be added in order to get a good approximation of what's going on. So what we're going to do is, since the first eigenvalue serves as a proxy for the rest, we're not going to worry about all the other eigenvalues. We're just going to consider the first eigenvalue. And so what we're going to have is a scree produced at every time, because every time output is going to have its own EOF data, but we're only going to pick as the proxy for that data we're only going to look at the first eigenvalue for every time, which means that the output that we care about from each of these different EOF analyses is going to be the first output, or sorry, the first eigenvalue at every output. And so what we end up with is a first eigenvalue. So that is one real number associated with every time output in the time series. Okay, so we take the first eigenvalue series, which is just this first eigenvalue from the normalized scree. And why would we do this? Well, times with a large first eigenvalue indicate times of good agreement across the runs, because if the first eigenvalue, say at output 1, is 90%, it means that most of the variance, 90% of the variance, is captured by only one EOF, right? So that means there must be a lot of agreement across the runs. Likewise, if the first eigenvalue was 0.1, then you'd know only about 10% of the variance was captured by a single eigenvector, a single EOF, and so there must be a lot of disagreement across the runs. All right, so here's our ensemble data sets. We're going to take our eigenvalue, first eigenvalue from each time, give us our time series. Okay, so that was all to set this up, okay? So here we're going to use a Seiche in a box. All right, so you can see that I was using this because these are hopefully familiar to you if you've seen the other videos. But we have this first eigenvalue series, and this is basically a density difference that's been tilted in a box, and it's sloshing back and forth, right? So if you just watch the top for a second, there's not a lot of outputs here because the outputs have not been, the outputs are only occasional compared to the computational outputs that aren't represented by outputs to the density field for storage purposes. So basically this is rocking back and forth and sloshing and jostling, whatever term you want to use. You imagine oil and water in a closed container, and you tilt it, and then it tilts back and forth. But of course, in this case, the density difference between these two layers is much smaller than the difference between water and oil, and you get a lot of effects that you wouldn't see with such a strong density difference. And so you can see that this mixing occurs, but it's over a wide area, and this sloshing back and forth very eventually gets worked out. Okay, and you end up with instead of a sharp density profile, this gets smoothed out into a more gradual transition from the dense to the less dense. Okay, so that's the Seiche that's going on at the top. These are 3 different runs, right? So remember, we're talking about ensemble members. This was actually done over 100 ensemble members. I'm only showing 3 because 3 is easy to visualize compared to 100. But at the bottom here is the result of that process I just indicated here, where I found the first eigenvalue series over the 100 runs, right? So I'm only showing 3, but there's actually 100 ensemble members, and I've taken the first eigenvalue series in the process from the process just described. Okay, so as we go through here, you can see that this time series, this first eigenvalue series, will show you times of agreement and times of relative disagreement. Okay, so agreement, a little bit of agreement, a little bit of disagreement, right? But you can see here that there's actually much more disagreement. You can see the difference between this and this, and this and this, and now even more disagreement, because of course you have this thick, relatively undisturbed area here of the dense fluid, and of course that's not the case in either of these cases. And then kind of the all-time low here, where you can see that, for example, there's this jet of material being injected up here, where of course there's still very less dense fluid here. There's still this dense area here, and of course there's no corresponding areas in the outer two, and so there's a lot of disagreement here. So it's below 0.1, and then as time goes on, as the mixing leads to a smooth transition from dense to less dense, you can see that the agreement goes up, generally up, until you reach this state that they all look pretty similar. Okay? And so right here is identified as a time when they're very much in disagreement. Well, why would we care about that? Well, it so happens that this is a time when there is energetic mixing, but the gradients have not yet broken down completely and smoothed out, right? So if you're familiar with the nomenclature of salmon, that is the author salmon, not the fish, you'll see that here the gradients are maintained, and this would be stirring as opposed to mixing, right? So stirring, and so on. And so there's still stirring and mixing starting to occur, mixing meaning the smoothing out of the gradients. But you can see that there's a transition here from just a pure stirring regime to stirring and mixing, which leads to a lot of disagreement, to eventually fully mixed and not much stirring. Okay? So that is the idea, and what has been identified here is a time when there's a lot of disagreement, and of course you can see lots of fine scale structure. This is very interesting stuff. So even if you're only looking at one of these, you would see, okay, that's cool. Yeah, that's interesting. And look at this time. And look how much is going on here. Certainly there's something going on here. Certainly something going on here. But lots of fine scale structure here. And then it's getting smoothed out. Okay? So clearly in this case, the first eigenvalue series indicates times of both agreement and disagreement. The disagreement was strongest at a global minimum. We've tried this on many data sets, and the results are always easily explained. Okay. But more testing is needed on production scale ensembles, but very few people do these. So this is a good tool. We have high hopes for its use later, but frankly, so far we've seen it done on tutorial data sets such as these, and we want to see it on a giant ensemble and see what it says. But until someone does that, including, maybe we'll do it. But the point is, this is still at the stage that we need to see it done on more data sets, and in particular data sets that are being studied already for other reasons. Right? We want to confirm the usefulness of this method on production scale ensembles. So that's the first eigenvalue series, and we'll keep you posted with more news on this as we progress through our research. Thanks for watching.